Querying a search index for objects similar to a given object is a common problem. A user who has just read a great news article might want to read other articles similar to it. A user who has just taken a picture of a dog might want to search for dog photos similar to that picture. In both of these cases, the query object is turned into a vector and compared to the vectors representing the objects in the search index. Facebook contains a lot of news articles and a lot of dog pictures. How do you index and query all that information efficiently? Much of that data is unlabeled. How can you use deep learning to classify entities and add more richness to the vectors? Jeff Johnson is an engineer at Facebook. He joins the show to discuss how similarity search works at scale, including how to represent that data and the trade-offs of this kind of search across speed, memory, usage, and accuracy. Spring Framework gives developers an environment for building cloud-native projects. On December 4th through 7th, Spring One Platform is coming to San Francisco. Spring One Platform is a conference where developers congregate to explore the latest technologies in the Spring ecosystem and beyond. Speakers at Spring One Platform include Eric Brewer, who created the CAP theorem, Vaughn Vernon, who writes extensively about domain-driven design, and many thought leaders in the Spring ecosystem. Spring One Platform is the premier conference for those who build, deploy, and run cloud-native software. Software Engineering Daily listeners can sign up with the discount code SEDaily100 and receive $100 off of a Spring One Platform conference pass, while also supporting Software Engineering Daily. I will also be at Spring One reporting on developments in the cloud-native ecosystem. I would love to see you there and have a discussion with you. Join me December 4th through 7th at the Spring One Platform Conference and use discount code SEDaily100 for $100 off of your conference pass. That's SEDaily100, all one word, for the promo code. Thanks to Pivotal for organizing Spring One Platform and for sponsoring Software Engineering Daily. Jeff Johnson is a research engineer at Facebook. Jeff, welcome to Software Engineering Daily.
Hello.
So today we're talking about similarity search and specifically where that applies to images and videos and how you do that at scale. Before we get into that, explain what similarity search is.
So the basic idea behind similarity search is that there are a lot of real world entities, that humans can interpret reasonably well. For instance, paragraphs of text or sentences or fragments of audio or, images or videos. And humans have an intuitive sense of, what, pieces of text are actually similar to each other in terms of meaning, not just in word content, or what images are similar to each other in terms of meaning or, visual features or, such things. Of course, with say traditional database systems, a machine is rather mechanically comparing the, similarity of, fragments of text or distance, just based on raw, pixel difference or, things like that. Your machines are, reasonably good at that. But what's definitely more complicated for machines to do is to try to take some of that human sense of, what images are similar to each other visually, what pieces of text, mean something similar. And, perform, checking based on distances to find, similar kinds of content to, something that you're interested in. So similarity search is, basically a mechanism, that is used in conjunction with, systems which can come from machine learning or AI or whatever, which generate these, representations of, what an image means or what a fragment of text means. And then you can use, similarity search techniques to sort of find similar, pieces of content to that.
When we're talking about user level applications or developer services, internal services at Google, or sorry, at Facebook, where would a similarity search mechanism be useful? What kinds of, if I'm building an application at Facebook, or if I'm a user, where would this ability to be able to search images that are similar to other images be useful?
It would certainly be useful in terms of, trying to detect, say spam, like in forms of images that people, like are uploading. It's also useful, for say, like you get like recommendations in your newsfeed in terms of, pages you might like or other videos that you, may potentially want to watch. Some of those are based on like embeddings of, what the pages represent, which we can get into later. Things like, product recommendations if you're, browsing like a marketplace of items, finding things that we think you are similar to, things that you've like looked at, before. So it's not really just about like, images or video. It's really about, sort of like assigning similarity to like real world, like concepts and things.
Okay. So I guess, I understand that was that, if you took like an article and you wanted to find articles that were similar to it, that's certainly an application of similarity search that I understand. I thought that the paper that I read was mostly about similarity search across images and video. Was I mistaken, or is this? Are we talking about the span of kind of all entities?
So the paper that I worked on with my colleagues who are in Facebook AI Research Paris, Matthias Duz and Hervé Gigou, that was, based, like the similarity search is basically like a technique. We applied it in that paper to like images because some of the largest publicly available, databases, containing like these high dimensional vectors that you use similarity search on happen to be of images. So for purposes of, publishing in the research world, you want to present results on publicly available data sets. You can present your numbers and other people can try out, like similar things. But the concept, like as it's generally applied, works equally well for, text and, like many other entities. Mm-hmm. And, so like at Facebook, it's, like, it's probably, like finds, like more current use, for, fragments of text or, concepts like, like people, like you may know, or, pages you may be, interested in, or products you may be interested in, than so much, constantly, comparing like, videos for search, even though we are, like using that as well.
I think of search as building an index from a data set and then building a way to query that structured index. Describe each of those parts of search as it applies to similarity search, just at a high level, and then we'll get into the nitty-gritty details.
Sure. The first thing is that you need a system to actually, generate the representation that you are going to index. For similarity search, similarity search works on mathematical vectors, sort of like high dimensional vectors. Imagine like a list of, like, say, 100 floating point numbers that represents a point in 100-dimensional space. We can get into like how those are actually, constructed from images or fragments of text, like later on. Now, the problem with, like these high-dimensional vectors is, the so-called cursive dimensionality. If you think about, say, like in 2 dimensions or 3 dimensions, if you want to find like nearest neighbors to like a particular point, there are a lot of like classical techniques, for doing that thing, many of which, find a lot of use, say in like, video games, for like, graphics or physics. You have like binary space partitioning trees, you have like, KD trees, you have, like, typical techniques to kind of like, divide and conquer and be able to quickly find, given a point in like 2D or 3D space, what the like nearest points like around that are. But this typical concept, definitely breaks down when you begin talking about 100 dimensions or 1,000 dimensions. If you think about like high dimensional spaces, like a square has, like 4, sort of like line segment faces. A cube has 6, 2-dimensional faces. A 4 cube has 8 3-dimensional cases. Get all the way up, talking about like 100-dimensional like hypercube. You have like 200 faces, each with 99 dimensions on either side. So like if you wanted to do something like a binary space partitioning tree, if you wanted to, say like, okay, I'm going to put a hyperplane in this space and try to, put all the points either on one side or the other side of the hyperplane, your nearest neighbor almost likely will lie, could very well lie on both sides of, that space. So, the typical like high dimensional technique, which works like pretty well up for, like up to like 10 dimensions or 20 dimensions, is the so-called KD tree, but that definitely like breaks down. It'd be like way, to actually index and use like a KD tree for these high dimensional vectors, you would spend more time, traversing the index than it really would be just doing like a brute force comparison. So this is where like similarity search, comes in. So there are a variety of techniques doing this. One that's been, like pretty popular for the past like 15 or 20 years is this thing called locality sensitive hashing, which we can get into in detail if you want. But much of the stuff that we're concerned with is has like a like a geometrical interpretation to it. It's called this product quantization thing. And what we do is we take these high dimensional vectors. They're very big to deal with, but we sort of like break them down and partition them into different buckets, and we sort of like compress them. And we build, sort of like a 2-level index of this. And then, given, some like query point in this like high dimensional space, there's a mechanism that you can kind of like, go in and, find like which bucket we think or which buckets your like nearest neighbors may be. And then you do kind of like a quick scan over, the vectors, which we think or potentially contain your nearest neighbor.
Yes. Okay. So I want to zoom back a little bit for people who are less familiar with this space. There is this concept of turning things into vectors and then doing similarity calculations on this. And this is not as complicated as it might sound to some people. Like I took a class in college that's really stayed with me where I'd say the most fundamental thing that we learned in the class is it was about information retrieval. But the most fundamental thing I learned was, you could take basically any document, turn it into a vector, just a kind of a measurement of, for example, the frequency of words that appear in that document. And then you can use those numerical representations to apply mathematics to things that don't seem like they could be mathematically calculated at first. If you take a news article and you want to find all the articles that are related to it, that's going to seem like magic before you kind of learn a little bit about vectorization, and then you learn about the types of similarity measurements you can do. Like if you just think about a article, if you can turn that article into what is an arrow in vector space, then you can perform similarity measurements across how that vector intersects with other vectors. And then you start to be able to use things like cosine similarity and do these geometric similarity measurements. And then it becomes less mysterious. Maybe you could give a little bit of a kind of overview of those kinds of strategies and why those are fundamental to this conversation.
Yeah, certainly there are a bunch of, sort of like concepts of like similarity measurement that you can think about. Probably one of the simplest things is not actually, say like generating, like a vector description of something, but just, generating a number. Like, imagine you take one piece of text and you take another piece of text and you look at sort of the, like the overlap or the intersection in terms of, like what words are, sort of common. Things like, Jacquard similarity or whatnot, like will, sort of like produce a number which tell you, kind of like the overlap of that. But what we're really interested in here is not just, sort of like a raw mechanical, description of how much overlap there is, like between, say like fragments of text or like, like you take an image and then you, like put like, something in it, you draw something in it. Well, like most of the pixels in the image are still be like relatively the same, except for the one little area. If you were to just, subtract the difference between the two pixels of, like all of both images, there would still be like, relatively like reasonable, but this becomes more complicated when we're really interested about concepts. So one of the things that, has been really, popular with the explosion of, like artificial intelligence, like, deep learning techniques and things like that are, now we have other ways, to have a computer sort of like distill down its idea of, like what real world content is. If, many of your listeners, may have heard about, so-called convolutional neural networks lately. Well, like a convolutional neural network, is used a lot, to determine, say like, take an image, like, is there a dog in this image or is there a cat in this image? It's able to sort of like, classify based upon like high level human concepts because it's trained to sort of like, recognize, which images have cats, which images have dogs, that sort of thing. But what all of these networks really do is they're taking an input, which is a very, big picture. If you imagine, say, like 640 by 480 pixels by like RGB, say like 3 bytes per pixel, like you can view that as a vector. It's a super, super high dimensional vector. But what if you were to run that through a convolutional neural network, it kind of like distills down to like a much smaller representation, say like 1,000-dimensional representation, which is kind of like the essence. I think that, some people have, termed this kind of thing like a thought vector. It's kind of like a distilled representation in like this high-dimensional space of, say like what this image like represents. You can do similar things with, text. Like, there are techniques, if you may have heard of, something called word to Veck, which is like a way to build these so-called like embedding vectors from like fragments of text. These are other, techniques that have been used a lot, recently in like the machine learning community. If you sort of like, take, say, sentences, and you look at sort of like the co-occurrence of, like certain words and like, the sentences, and based on, like you scan like a bunch of text and like words which, say like tend to co-occur in similar context, you sort of like push them closer together in high dimensional space, and words which, have nothing to do with each other, you tend to like, push them apart. If you do this kind of thing like many, many times, you kind of wind up with this like high dimensional representation of what words mean. There are interesting things where people have done with like word to Veck style models where you can take, a vector representation, say for the word king, and you take a vector representation for the word man and woman. If you take, like king minus man plus woman, with that, the point that gives you actually happens to be, relatively close to, say the word queen. So these high dimensional spaces, do actually encapsulate, some notion of meaning, for this.
Grammatech Code Sonar helps development teams improve code quality with static analysis. It helps flag issues early in the development process, allowing developers to release better code faster. Code Sonar can easily be integrated into any development process. Code Sonar performs advanced static analysis of C, C++, Java, and even raw binary code. Code Sonar performs unique data flow and symbolic execution analysis to aggressively scan for problems in your code. Just like battleships use sonar to detect objects deep underwater, engineers use Code Sonar to detect subtle problems deep within their code. Go to go.grammatech.com/sedaily to get your free 30-day trial exclusively for Software Engineering Daily listeners. Code Sonar analyzes your code, and it delivers a detailed report. The Code Sonar user interface provides all the information that you need to quickly understand the reports, follow cross-functional paths, understand cross-references, quickly navigate between files, and visualize large pieces of your code. Go to go.grammatech.com/sedaily to get your 30-day free trial and unleash the power of advanced static analysis. Thanks to Grammatech for being a sponsor of Software Engineering Daily. Well, I was going to ask for, this is not directly related to what we're talking about, but I've heard word to Veck discussed in a number of different interviews I've done, and this is something I'm still not super clear on. Explain what word to Veck is.
It's a means of, as I said, it's, like you take, fragments of text, you take, sort of like, combinations of words in that text, and based upon, like the context in which those words occur, you're either, you start off with, say like words assigned to kind of like random positions and like high dimensional space. And you're either, based upon, the way that you see, these words occur, you're either, like iteratively, pushing together or pulling apart, like these, vector points in like high dimensional space, based upon, things that you encounter. It's, like there are lots of ways, to decide how you want to, like what this context of, like sentences is, like how much you want to push them together, or, like push them apart, that sort of thing, but it's basically an idea that you look at, like lots of different ways in which, like these words occur in the real world, and you like do all these iterative steps to kind of like, push around, like these vectors, and eventually you wind up with, similar concepts, together in, like high dimensional space, and, concepts which are not similar, like further apart.
So it's a library for doing text, kind of turning text into vectors so that you can do calculations, machine learning stuff on top of that.
Effectively, yeah.
Okay. All right. Well, okay. So now we've kind of given people an overview for how we turn information into vectors. So as far as images or video, you mentioned this curse of, what is it? Curse of dimensionality? Is that what you said?
Yes.
So what do you mean by, I think that kind of gives us an impression for why this is actually a really hard problem, is the number of dimensions that a vector can have. If you turn an image into a vector, to accurately represent it, you might need a lot of dimensions. But explain kind of what that term dimensions is referring to and why these images have so many dimensions.
So the dimensions, it's the same concept that you have of, say a piece of paper, is sort of like a two-dimensional space. You can draw on it, like you can move up or down or left or right. 3 dimensions, it's the real world. Like you can, like go around in like 2 dimensions and also up and down. It's the same concept, like 4 dimensions, like you could, like in real world, we could add time as like a 4th dimension we could think of. You can continue this process, it's kind of like a mathematical notion of, like what a dimension is. And you can, think about like 50 dimensional spaces or 100 dimensional spaces. If you want to see what that actually looks like on paper, if you were to say like write down 50 different numbers, say like 1, 3, 7, -1, like whatever, that, kind of defines a point in like a 50 dimensional space. This is this is a vector. It's basically just a list of numbers that, or coordinates, like for some point in a high dimensional space. Mm-hmm. So, like these machine learning processes that we've, like talked about, at the end, they're spitting out, say like 100 numbers or 1,000 numbers, which is this, kind of like abstract representation of this piece of content in a high dimensional space. Mm-hmm. So, then the problem is that, well, given like a particular piece of content, like what are other pieces of content that, are, that happen to be like relatively close by in terms of that representation, meaning that they are similar in some notion. Whatever the machine learning, process happened to do with it, it has some notion of like, what's similar or what's dissimilar. Mm-hmm. So, given a point, given say like a list of 100 numbers, which is a point, which is a representation of an image, and then given, say like a set of 1 billion other images, how do you find, say like your 10 nearest neighbors?
Yeah, right. So I get that. I get that you want to do nearest neighbor, KNearest neighbor. By the way, for people who don't know, an abbreviated, dumbed down explanation of KNearest neighbor is you take a vector and you have a large set of other vectors, and you set k. Let's say you want to do k equals 3, and you want to find the 3 nearest neighbors. You want to cluster you can cluster all of this data into kind of a vector and then the 3 nearest neighbors to it. I might be bastardizing that explanation, but so I understand why you want to do that in similarity search, because if somebody enters a query for let's say their query is an image of a cat, you want to be able to return the k nearest, like let's say you're going to have 10 search results, you want to return the 10 nearest neighbors that are similar to that cat picture. So I understand why you need to do k-nearest neighbor algorithms across this data set, but there's also the classification step. So you have a step of classifying these vectors somehow, or for some reason, I'm not quite clear on that. So maybe you could give any more color on the k-nearest neighbor question that you want to, and then explain why classification is relevant here.
Classification and, like what sense? Are you talking about building the index or?
Well, I just remember, I read about it in the paper, but I didn't quite understand what was being referred to. So there was like basically a part of the paper where it said, okay, there's 2 main steps. Oh, actually, this was not the paper. This was like the more digestible blog post about the paper. But it was like, there's 2 steps we need to do: classification and k-nearest neighbor. And I didn't quite get why classification was relevant.
I think I remember the blog post. The classification, may have been, I don't know if it was discussing, say, the kinds of things that you do with, say, convolutional neural networks and images, and determining if this image contains a cat or a dog or, something like that.
I mean, is that helpful? Would you run all these vectors, all these images through, some sort of system that would say, okay, this has a 90% probability of being a cat picture, and then that classification can be added, like that probabilistic classification can be added to this piece of data, and then that's helpful when you're doing the K-nearest neighbor algorithm?
So the classification, I guess if if we're thinking about the same thing, say you took this network, which classifies, whether something is a cat or a dog or whatnot, and you chopped off that last little bit. We don't actually care whether something is a cat or is a dog. We care about, say, what high-level features made the network think that, in combination, this picture has a cat or this picture has a dog. Sort of like a little more like abstract, from that. So the network, may have been originally designed for like category classification, is this a cat, is this a dog, whatever. But in the act of doing so, it's kind of like generating for itself these like high level descriptions, which are these like high dimensional vectors of, what is actually, contained inside this picture.
Oh, okay.
So, you kind of like cut off the head of, you can take one of these classification networks and you sort of like, cut off the head of what's inside of it. This may have been like the blog post. You can imagine that in a typical database, you have like actual, say like a SQL database or something. You have actual fields, where someone has gone in and said like, this is a cat, it's a black cat, it's a black cat, that's, like 20 inches long or something like that. Those are a bunch of, and you can sort of query based on, combinations of, like those fields. In our case, what we're looking for is, maybe, we're looking for pictures of cats, but we're looking for pictures of cats which are very similar to this very cute black cat, that I have in this one particular picture. Well, the network itself was not, trained on, was not trained on being able, necessarily being able to categorize like, exactly similar cats. It was trained on being able to, classify, this thing is a cat versus not a cat. But like internally, it still has this kind of like high level representation of, like what's actually in the image. And we sort of like, take
more dense representation.
Yeah. It's it contains, many things about, say like, visual textures, which might be in the image, like where things are located in the image, that sort of thing. These networks can generate that.
Right. Okay. So is this kind of like the layers, like different layers of a convolutional neural network can present numeric representations of different aspects? Like you're talking about textures. I think of textures as a little bit higher up the neural network or further down the neural network pathway from like edge detection. Like first, the earliest layers of a CNN, you would have edge detection, and then the edges might abstract into textures, and then those textures could be something you would represent in a vector that would be applicable to higher level stuff in the CNN. But also, it's just useful if you just want to build a really high dimensional vector to later on do K-nearest neighbor on. Is that accurate?
Yeah, I mean, it really, what you mentioned, individual layers in the network, at each layer, there's a mathematical description, sort of like this high dimensional vector that is, what it thinks this, like say image is. Like low down in the network, some of the early layers, they're very like low level features. The low level features in a ConvNet, tend to look like things like, like edge detectors and things like that, say like oriented edge detectors. If you were to take that as like a high dimensional representation, and it is, giving you, it's spitting out a list of numbers and passing that list of numbers to the next stage, that's like a very low level description of that. But we're interested in kind of like higher level descriptions, not like, oh, there happen to be a bunch of, like diagonal lines like in the image. We're interested in, well, this thing looks like cat fur, not like dog fur, say. So, the higher up you go in the network, the deeper and deeper that you go, these individual layers are spitting out like, kind of more higher level, descriptions of an image, things which in kind of like a weird way, might actually correspond to the way that, humans, like tend to think about, the world.
Yeah, that's quite interesting because so that's to say that at each of these layers of the convolutional neural network, you could have kind of more, I don't know if it's the right word, but a little more granularity or different degrees of granularity in terms of how you're looking at this overall image. And, I could imagine if you really wanted to get super accurate, well, I don't know. So like if I'm doing KNearest Neighbor, is it going to be more accurate if I'm taking into account the vector representations of all of the different layers of a convolutional neural network, or is there some sort of diminishing returns? Should I just be using the kind of layer where you're talking about like the I don't know, the more fuzzier or the higher level contours of this image? Are there diminishing returns, or am I always going to get more accuracy if I'm using more data from different layers?
Well, it's like the idea is kind of like what is your notion of like similarity? There's some kind of I guess like co-design which has to like happen here. It's sort of like a garbage in, garbage out thing. It's unclear, say like what kind of ConvNet you would actually want to extract like visual features from an image. You might have to try a bunch of experiments. You might have to try like, say, deeper layers or shallower layers in the network to kind of see, like whether it's, spitting out something that when you go through this K-nearest neighbor process, gives you, what you want when you're asked for like a picture that's similar to this like really cute black cat. So it's, like it's not like that necessarily the case that more data is like always good.
Right. Okay.
That could be kind of, like meaningless.
Yeah, I think I have a good example. So like those kinds of pictures where you have like blueberry muffins or what is it? Blueberry muffins are a kind of dog. You see these memes where it's like the neural network like can't tell the difference between like legs and hot dogs or poodles and blueberry muffins. You know what I'm talking about?
Yeah.
Yeah, so like those, I guess, okay, do you, maybe in some cases the similarity algorithm should be identifying these as similar because like, okay, they kind of do look similar. If that's, your metric is just like, okay, this dog looks like a blueberry muffin if you squint, but if you're actually trying to detect, is this a dog or is this a blueberry muffin, you would, and if that's your kind of the way that you're looking at the similarity, then for each of these different perspectives that you want your similarity mechanism to have, you would want, I guess, different layers or different different layers to be stressed, to be emphasized in that similarity mechanism. Is that accurate?
Well, like I guess, like you mentioned something, a lot of people have done work on this, so-called like adversarial examples for like network. Like, I could take a picture of a cat and I could sort of like tweak that picture of a cat in very unperceptible ways, that before it thought this was a 90% chance that this, picture was a cat. And now it thinks it's a 90%, chance that this, like picture was a dog, even though to a human, it still like looks like a cat. These, I mean, to some extent, like some of these are like, contrived examples where you are actually looking at the mathematics of the network and you're sort of like pushing this image in the direction that it would begin, thinking it's a dog. It's taking like all of these real world concepts of cat and dog and whatnot and sort of like shoving them all together and trying to build sort of like a map in this like, 100-dimensional or 1,000-dimensional space. And if you just make like little moves in that 100-dimensional or 1,000-dimensional space, you might, like jump over a cat to dog to giraffe, like to whatever. The idea is that, still like on average, looking at things in the real world, like it's going to give you, say like, hey, this is a reasonable chance that, like this is a cat. It's not going to work, say like 99% of the time or 100% of the time. If we had a system that could do that, that is basically, what AI like really is. But, like unfortunately, like all of these systems, like they work reasonably well, but they, don't work at, sort of like, human level, like accuracy for these things.
The process of troubleshooting bugs can be tedious and inefficient for developers, especially as they push more and more code to production. The unlucky developer assigned to bug duty may get bombarded with error alerts and spend hours figuring out which errors to address first. They might have to deal with logs to piece together what happened, or even spend time reaching out to other engineers on their team for help. Bugsnag improves the task of troubleshooting errors by making it more enjoyable and less time-consuming. For example, when an error occurs, your team can get notified via Slack, see the diagnostic information on the error, and identify the developer who committed the code. Bugsnag's integration with Jira and other collaboration tools makes it easy to assign and track bugs as they are fixed. We have a special offer for Software Engineering Daily listeners. Try all features free for 60 days at bugsnag.com/sedaily. Development teams can now iterate faster and improve software quality. To get started, go to www.bugsnag.com/sedaily. Get up and running in 3 minutes. Airbnb, Lyft, and Shopify all use Bugsnag to monitor application errors. Try all features free for 60 days at bugsnag.com/sedaily. Thank you, Bugsnag, for being a sponsor of Software Engineering Daily. It's much appreciated. So let's get into some of the scalability, systems design questions, because I think we've kind of outlined what this problem is. So you mentioned that the traditional SQL representations, if you're trying to represent these vectors, these high-dimensional vectors accurately, traditional SQL representations are probably not the best data structure to use. So why don't you explain why that is and what representation or database you want to use for this problem set?
Like there is geometric data that, people are indexing today in databases, say, like GIS, like databases, which may contain, 2D or 3D information, like, things like maps or, positions of, things, like on the surface of the earth, that sort of thing. A lot of, traditional databases, like have index types which are built around this. Like one sort of like classical index type, for instance, is a quad tree. You take your points and you begin, sticking in like, vertical lines or horizontal lines and sort of, build a tree by like, partitioning things. Like everything that's on the left side of this line, goes in one branch of the tree. Everything on, the right side of this line, goes in another branch of the tree. Those kinds of like indices, work very well, for like 2 dimensions, 3 dimensions, like on up. The extension of, a quad tree is a, kind of like a so-called, KD tree. You can, begin inserting, planes in like higher dimensions. This technique works really well up into probably about like, 20 dimensions or so. But that's where this, kind of like, cursive dimensionality, thing comes up. And I believe actually like some SQL databases, do have, what are effectively these KD tree indexes that you can actually use on, sort of like high dimensional data. But as you begin adding like more and more dimensions, like every line or every attempt to sort of like split the data set into 2 and kind of like, subdivide, the problem is that your nearest neighbor, if you, say like, take a plane and some space, your nearest neighbor it's probably fairly likely your nearest neighbor will happen to be like on either side of like a particular plane. This is the cursive dimensionality. Like I think I mentioned like a while ago that a square has, like 4 sides to it. A cube has 6 sides to it, but a 100-dimensional hypercube has, 299 dimensional sides on it. Like chances are you'll have to check like, most of those. So, this kind of like, brute force, I guess this kind of like divide and conquer scheme, really does not work well in high dimensions. Mm-hmm. So there's always brute force search. You can always, like go down, if you want to find your nearest neighbor among, say like a billion vectors, you can always like brute force it, but you want to build something that you can perform queries, like relatively fast. And the way that people get around this is by throwing out the idea of that this query is exact, being okay with the idea that this query is actually approximate. Say like 80% of the time, I'm going to return you your true nearest neighbor. You might occasionally miss your nearest neighbor, but, given that the input to this, the similarity search input, these high dimensional vectors are kind of this, fuzzy abstract concept anyways. chances are you may not actually be missing that much, by, not actually giving you your true nearest neighbor.
I'd like to frame this problem a little bit more in terms of the two steps of a search engine, which is building the index and serving queries from the index. So let's just talk about building that index. Can you talk a little bit more about the engineering behind building an index for high dimensional vectors? Like, where do we want to keep this data? Are we going to keep it on disk? Are we going to keep it in memory? What kinds of processing capacity do we need? Kind of what are the distributed systems problems? Could you just kind of pull on that thread a little bit?
Sure. So the way, like later on we can go into detail about, what our index actually looks like. But, like we use this technique that you can read about in our paper, like, perhaps look in our blog post. That's called, sort of like an inverted file with using product quantization. But the basic idea is that it is trying to like partition the data set. So I have a billion vectors. You're trying to, divide up those billion vectors into, say like a million different buckets. So each bucket has like 1,000 vectors. And then, but the thing is, like, if you think like a billion vectors, originally these were, say like single precision floating point numbers, say like 4 bytes each. And, there happen to be like 100 dimensions. So that would be, say like 400, that would be 400 gigabytes of data to actually, store like the raw, like database. Like this is, like definitely a lot of data that, can barely, can hardly fit, say like in memory on like a single machine, like is even kind of like hard to, manage on disk and whatnot. So, like because we're okay with like approximate lookup, what we try to do is actually compress these vectors. So we don't need, like every vector, as I said, if it were 100 dimensions, 4 bytes per dimension, we maybe don't need, like 400 bytes, like per vector. We may be able to get away with, 20 bytes per vector or 40 bytes per vector. So we take the vectors and we compress them in a way that we can kind of approximately reconstruct what the original vector was, but it's kind of like a lossless, if you think about like, JPEG or image compression schemes, this is kind of like a lossy, compression scheme, like for these high dimensional vectors. So we compress all the vectors and we put them into like a bunch of like different buckets. And then when you want to, in those buckets, are kind of like all clustered around different points in this like high dimensional space. So if you have a vector that you're interested in finding the nearest neighbor, if you have a point in this high dimensional space you're interested in finding the nearest neighbors for, you first find what are the closest buckets that this point, like may lie in. And then for those buckets, you scan, say like all of these, compressed vectors, to get a sense of, what your actual like, nearest neighbors, could be. So this is something that you can put this on, like you can put this on disk, but there's, if you want this, to, process at reasonably interactive rates, because there's still like a reasonable amount of like brute force, searching that you do. Like for each bucket, as I said, if you had 1 million buckets, 1,000 vectors per bucket, every bucket that you visit, like your brute force scanning, like 1,000 vectors, kind of like comparing to find out what your nearest like neighbor is. There's still like a lot of brute force scanning, that's occurring, like way more than say would be the case with a typical relational database where you're just, like traversing an index and you're only, sort of like hitting, like a relatively, small number of rows or things in this index. We're definitely scanning like a lot more data, like, when we, try to look up a particular entry. So, this is a good reason to kind of like, try to keep this thing in memory. And given the, compression of the vectors, that actually, allows us to sort of like, compress, what originally would have taken 400 gigabytes into something, which could take, say like, 10 gigabytes and could, like reasonably fit into memory.
Does it become too costly in any way to keep it all in memory? Actually, well, I know this is a relevant question because there are 3 metrics of interest that you explored here, which was speed, memory usage, and accuracy. How do these 3 things trade off against each other?
So, like the accuracy is definitely related to, like where I was talking about these buckets that you have to visit, is definitely related to how many buckets that you want to visit. And it's also related to how compressed like these vectors are. But if you like imagine if you were to compress the vectors less, that means that they would take more memory, whether on disk or more storage, whether on disk or in memory. But, like the actual query against them would be more accurate because you have a more accurate representation of what the original vector was. But because they are like less compressed, there's kind of like more data that you have to go through and more calculations that you're going through. So it would sort of like, take more time. So there's kind of like, like a three-way trade-off, between how fast you want a lookup to be, how accurate is that lookup, and, like how much memory your overall like, database is using. Like a lot of these trade-offs, come in different ways of actually like building this index or say like, compressing these vectors. And there are, tons of different techniques, like for doing that. But for certain applications, you may care more about accuracy than anything else. So you may not actually want to compress the vectors at all, but you still want to build some sort of index around them. For other applications, you may want to be able to get like a result in, say 100 microseconds. In this case, you really need to sort of like, touch as little memory as possible and do as few calculations as possible, but you're definitely going to, potentially suffer in accuracy a lot as a result.
Now, how consistent is this? If I query the index twice, do I get the same responses?
Yeah. I mean, the calculations are like deterministic. It's not, it's not being like random or, but what is, potentially not deterministic is if you were to rebuild the index with like new data, the way in which it comes up with these like quantization schemes to compress the data, may be different. So the results that, you get then if you had, say like a database that would dynamically update and like, recompress the data, that sort of thing. You could change over time, but, given like a fixed like index that you've built, like it will give you the same results every time.
Okay. And so I know you've kind of alluded to this and talked about it a little bit, but can you just explain once again the process of serving a query?
So one reason, so I, worked on an implementation which actually uses GPUs or, graphics processing units. And one reason it works out like pretty well for that is we need to perform a lot of like mathematical calculations, like in finding, like nearest neighbors. So like if you think about a way to sort of like look up brute force like nearest neighbors, given a vector and then given a bunch of other vectors you're comparing it against, like one way of doing that is by doing like a matrix vector multiplication and then, kind of like, taking like the top, the 10 highest, like results from that. What works even better is if you actually have a batch of queries, say like, and I'm not just, querying like a single vector, give me the nearest neighbors. I'm querying 1,000 vectors, give me the nearest neighbors for each of those 1,000. That turns that like matrix vector multiplication into a matrix multiplication, which is like a lot more efficient at using the resources, the computational resources, because it's able to like, reuse the data that you're like loading and traversing when doing that. And if there's one thing that GPUs are great at, and that's, the main reason, I guess, why NVIDIA stock has been going up is because GPUs are really excellent matrix multiplication machines. And pretty much all of, like AI, deep learning, machine learning is effectively matrix multiplication. So they're really great at, doing that. They're really fast at doing that. So there are a bunch of like matrix multiplications we have to do, and then a bunch of like scanning of like a list of memory. Another thing that GPUs are good at, like relative to the CPUs, is that they have like really high memory bandwidth. Like the GPUs you can get, like the NVIDIA Maxwell class GPUs have, like roughly 300 gigabytes a second of memory bandwidth, compared to, kind of like top of the line, like CPU machines where you'd, probably be lucky to get, like 50, 60, 80 gigabytes a second. So they're really great at scanning lots of memory. The thing that GPUs are not so good at is, like the latency aspect, or if you had a bunch of like, branching in codes or things like chasing like linked list or, things like that, things which are very sequential in nature. GPUs are very bad at that sort of thing. But, the things we need here are being able to scan lots of memory really fast and performing fast matrix multiplications. GPUs are great at, so we, like implemented this, stuff on GPUs as well. And, effectively it gets a 5 to, like 10x speed up over like the CPU, but there's no reason why you can't use a distributed form of CPUs to do the same thing. And there's no reason why you can't actually, put this on disk and then, have, to scan through a bunch of these lists on disk. But of course, like it'll be a lot slower because, a disk, the speed at which you can scan through data on the disk is, much lower than, the speed at which a GPU can, scan through its main memory.
The time has flown by, and I want to zoom out and give a little bigger picture for how this fits in to Facebook, because this is a Facebook research project. You work out of New York at the AI, I guess the kind of AI labs there. Can you explain how research at Facebook engages with the product engineering teams, how these kinds of breakthroughs make it into production?
Yeah, so I work for Facebook AI research, run by Jan Kun, who's also a professor at New York University. Like our basic mandate from Mark Zuckerberg is to be a pure research lab. Like no one is like necessarily coming to us, to say like, hey, can you get this feature in this product, or hey, we need like help with this particular thing. There's a sister team at Facebook called Applied Machine Learning, or AML. Those are the people who are actually, work with a lot of the product teams to get, like new, research components or, like other such things like into actual products. But we also like internally at AI research, we do actually, like talk with, like product teams, because, to have a research lab, which is actually, successful, you need to have some practical applications at the end of the day, for your work. And it's also, quite fun and enjoyable to, turn around and, like help a product team out with something. And, like before you know it, it's, released to, like 2 billion people. But, sort of like our primary focus is not necessarily to work on actual, like, products, even though we do, like do that occasionally.
What are the opportunities for improvement for the Similarity search project as it stands today?
So from a research perspective, certainly the opportunities for improvement are, better ways of making this like approximate search, because, it's lossy, it's approximate, it doesn't necessarily give you the right results, better, for the same speed or the same like memory consumption. That's like there are a variety of like, techniques that, we're sort of like, working on to do that. There's the systems research perspective, which is, how can we implement this, these given algorithms like more efficiently on like GPU or CPU. And then, based upon that, it's, getting, like, well, is there some like, product group at, Facebook or Instagram or, like wherever that, has an issue that, could be, potentially solved, like by like, similarity search, or, something that could be improved, like by similarity search.
If there's somebody out there that's listening and let's say they're a researcher and they're working in related areas, either in search or machine learning, something like that, what are some of the other novel contributions that come from your research that people might be able to gain by taking a look at your paper?
So I think the main thing, and the thing I worked on the most, was getting the GPU implementation to work well. Like a lot of people have tried this sort of thing with like similarity search on like GPUs before, but one of the limiting factors is actually something quite mundane. It's say finding like being able to find what the k highest valued or like lowest valued like objects are. You think on like a CPU you can have like a min heap or a max heap or something like that. It works like pretty well. But this sort of thing is like really hard to parallelize. Probably actually what I spent the most time on last year was not all of the this product quantization stuff or all these crazy similarity search things. It's just getting this fundamental algorithm of like, how do you find like the top K or the bottom K, valued, things to work well on like a GPU? This has been, the problem that, people have had with a lot of like previous implementations, because it's kind of like a fundamentally more CPU friendly algorithm. You think like the naive manner would just be, oh, you take your all your items and you just sort of sort them and you would take like, the top 10 or a top 100. The non-naive way would be to use, say like a min heap or a max heap. On a GPU, it definitely required a lot of effectively like hacking and trying to, deal well with the GPU's like memory hierarchy and, the fact that GPUs just have so much more like register memory than like, CPUs, to try to, squeeze as much out of that, to make that as fast as possible. And that's really the key, spending like months of time working on that enabled like the similarity search, like on GPUs, to really be like super fast. And it, effectively, gave us, like the fastest, similarity, search method.
Okay, last question, because I know we're up against time. This is some really deep research. And whenever I interview people about serious research, particularly when it's in the industrial domain, I like to ask, what's the difference these days between academic research and industrial research?
So I think, I have to admit, I've never, personally been in, a academic research setting, but most of the people, a good chunk of the people that have either been, like professors or postdocs at, various academic labs. Certainly, I think in, like computer science and, or, more specifically in this case, like machine learning, applied math as it involves like machine learning, because there's so much interest from industry, there's a lot more crossover in terms of, people who, may spend part of their time in academia and part of their time in industry and, go back and forth. I think like a lot of the research objectives have kind of like lined up in some ways between academia and like commercial research in these areas. But, certainly like in a commercial research environment, at the end of the day, like there are customers in-house, like who are interested in your products, whereas in an academic environment, you may be more fundamentally concerned about, say like what are the underlying mathematical reasons for why a ConvNet actually works, which is, something which a lot of people are, still interested in, trying to figure out. Like in our particular lab, we do have some people working on, some of the more theoretical aspects, but we also have a lot of people, interested in, like product applications and hearing about, the problems that people have in an actual like industrial environment, which can, feedback, sort of like more quickly to our more academic work.
Okay, well, let's close with that. Jeff, thanks for coming on Software Engineering Daily. It's been really great talking to you, and this is a fascinating project. I really enjoyed reading the material around it.
Yeah, thanks a lot. Hopefully it wasn't, it's definitely like a, rather, complicated, in-depth, subject, but, it's definitely an area which can, have a lot of real world applications.
Yeah, I mean, some days we do shows about, what's the latest like fluffy thing you built with JavaScript, and some days it's okay, let's get into the weeds and talk about how you build a large scale similarity search engine. So, we have a variety of stuff. It's perfectly fine to go deep.
It sounds good.
Okay, cool. Look for a job more efficiently with Indeed Prime. Indeed Prime flips the job search model and lets you find a job more efficiently even while you're busy with other engineering work or coding your side project. You simply upload your resume, and in one click, you get immediate exposure to companies like Facebook, Uber, and Dropbox. The employers that are interested will reach out to you within 1 week with salary, position, and equity up front. Don't let applying for jobs become a full-time job itself. With Indeed Prime, the jobs come to you. The average software developer gets 5 employer contacts and an average salary offer of $125,000 through Indeed Prime. It's 100% free for candidates. There are no strings attached. Sign up now at Indeed.com/SEDaily. Thank you to Indeed Prime for being a repeat sponsor of Software Engineering Daily. And if you want to support the show while looking for a new job, go to Indeed.com/SEDaily.
Wow.